Good afternoon, good morning, everyone. So welcome to the first edition of the 2027 Time Delay Systems webinar. And it's my pleasure to start with a talk of Keqin Hu. It's one of the pioneers on control of time delay systems and recipient of an IFAC Time Delay Systems Lifetime Achievement Award. And so next to the many influential papers of Keqin, he's also been very active in our community, in service towards the community, via many roles in editorial boards, the organizations of several workshops and conferences, and via by leading international collaboration projects. So I think that many of the people in our community, and especially many of the young people, benefited from the excellent service of Keqin to our community. I'm also sure that most of you know Keqin as one of the authors of the book Stability of Time Delay Systems, which is one of the most influential and most cited reference work in our domain. So Keqin, uh, thank you very much. I hear that you will give a talk about neutral equations. So if you are ready, you have the floor. So after the
Okay.
talk, we have a Q&A, and you can also already indicate questions in the chat if you like, and I will monitor that. Okay, go ahead, Keqin.
Oh, okay. Thank you, Wayne. Well, good morning, good afternoon, good evening, wherever you are. Thank you for attending this webinar. Today's topic is on neutral type system. So I will touch on sensitivity, some practical implications, and I will also talk about the modeling part of it. Now, neutral type time delay system, at least when it's restricted to be linear, uh, is typically written in this way. And there are some classical books, papers discussing that. Probably the best known would be two books by Bellman and Cook and Hale and Vudui Luno. Now, today we are going to explore a different model that's coupled differential difference equations that's written in this form. And not only is coupled differential difference equation, it is also of a special form that is one delay per channel. In other words, for each y, I call that as a channel. In the whole equation, there's only one delay. And it turns out it is always possible to write in this form. And it has its advantage in terms of some formulation, fundamental solutions, stability analysis. Now, the easiest way of thinking about this model would be through a process called pulling out delay. And this process is analogous to a pretty well-known process is called pulling out uncertainty by Doyle. The idea is this: when you look at the whole system, you isolate all the delays and take them out, except the input and output channel, and then you write the rest of the system in a state space form. Then after that, then you reapply all these delays, and they will appear as feedback channels. So if you do that, the part without delay will look like this, and the delay reattached will look like this. And if you apply this equation into these two entries, you indeed come back to that coupled differential difference equation with one delay per channel formulation. Now I want to talk a little bit about the history of this formulation. And actually, this formulation comes out naturally when you model practical system. For example, Kapkov and his collaborators as early as 1946 in former Soviet Union, they were modeling steam turbines. Another pretty well-known paper is by Brayton in modeling lossless power transmission system. And indeed, a lot of traditional formulation of neutral type of system cites those some of the examples, except that they reformulate that into a more traditional differential difference equation. More recently, the group led by Ross Vine wrote quite a few papers on Ward-Hammer or similar systems, and you probably can find those papers in his website. Now, in terms of analysis, the earliest direct analysis of this formulation is by Ross Vine in 1973. I'm aware of. Now, there are some other analysis. I wouldn't call those as direct analysis. For example, Hale and Huang, they would take a derivative of the difference equation, then constraining the trajectory within a manifold. So those kind of formulation are not that easy to handle if you want to do a stability analysis, especially if you want to do the Lyapunov-Krusovsky functional method. Well, when coming to a more modern time, one of the biggest promoter, I would say, probably the biggest promoter of this formulation is Ross Vine. I think through Silvio Niculescu, I heard a lot about his efforts. And especially in 2006, Vladimir Ross Vine gave a plenary talk on this formulation. And there are a lot of other scholars, for example, Amelia Friedman was, wait a minute, it keeps jumping along. Okay. Amelia Friedman using a tensor formulation, but in the spirit, it's in this break framework. Pepe and his co-authors has some work on this, mainly on linear aspects. Now, most formulation today will be concentrated on complete quadratic Lyapunov-Krusovsky functional, and this formulation has a potential of approaching the analytical limits. And I also work with Matthew Pete on SOS formulation along the same framework. Okay. Now, one of the important thing in neutral time delay system is associated difference equation. And if you take away the differential variable and the equations, this is a difference equation. In early 1970s, a couple of authors, Marino, Melvin, and Henry, made a discovery that says the upper bound of the real part of the spectrum is a discontinuous function of the delays in the multiple delay case. So that has a profound effect on the coupled differential difference equation. Indeed, the important implications are, first of all, The overall system can be exponentially stable only if the associated difference equation is also exponentially stable. Or you can say that in opposite way, the overall system is always exponentially unstable if the associated, I'm sorry, yeah, if the associated difference equation is exponentially unstable. Now, by exponentially unstable, I mean there's at least one characteristic root on the right, strictly right half plane. And also, if you can find a vertical line and all the roots of the difference equation are restricted on the left of this line, then all the roots of the complete system on the right of this line would be continuous. So that will be amenable to more routine analysis. So those are the fundamental things we need to keep in mind. Okay. So the important concept is strong stability of the difference equation. And that was formulated in 1975 by Hale. And later on, Hale and Badui-Luno gave a little bit more rigorous proof and added one more item. So let's go through this idea. It basically says there are three different statements about the stability of the difference equation. The first statement says there's a fixed delay, and those delays are rationally independent, and the difference equation is exponentially stable. The second statement says, now, let's imagine if you have a fixed set of delay, and I did not say whether it's rational or irrationally dependent, but you can allow some variation within epsilon range, and this epsilon is arbitrarily small. And the system, the difference equation is stable when the delays vary within this range. Obviously, this is a little bit more strict because within, no matter how small the range, you can always make all these delays rationally independent. The third statement says the difference equation is exponentially stable for all the possible delays. And that's obviously more strict. Now, Hale and his co-authors indicated these three statements are the same. They are equivalent. So that's a very striking statement. In other words, if the delays are rationally independent, then you can forget about the delay range or anything like that. They are just delay independently stable. The fourth statement is a criterion how to find such a difference equation stable. It basically says the first column multiplied by a quantity in the unit circle, the second column a quantity in the circle, but they may be independent, etc. Each column are like that. Then the spectrum radius must be less than 1. So that's a necessary and sufficient condition. Now, of course, if you want to actually calculate that, then that would be a daunting task because you have n quantities. They all need to go through unit circle, and that's not that easy. Now, first relaxation possible would be instead of within the unit circle, you say, well, I let it to vary within the unit disk. And that will bring us to the mu problem, in other words, the structured singular value problem. But that's still not easy. Mu is notoriously difficult to calculate. But if you relax that a little bit further, you come up with a LMI, linear matrix inequality, that look like this. For you can find S, which is diagonal, and this LMI is satisfied. Now, there is a more accurate LMI possible. That's by Bremer. That's inspired by 2D system, but I have not pursued that. It's not that easy to integrate into overall Lyapunov-Kulusovsky functional, but it may be pursuing in the future. Now, in terms of stability formulation using complete quadratic formula, Lyapunov-Kulusovsky functional, then it look like this. Basically, it goes through all the possible quadratic form. And if you discretize that, it will have a very big LMI, or not go through that, just flash through those. So that sort of will give you an idea what the computational requirements. But now let's look at some of the practical problems that is related to this sensitivity issue. The first problem I want to look at it is the Smith predictor. Smith predictor says if you have a system and I want to design a controller, and this system has a delay. Now, Smith said you can always use a controller that look like this. This GM is supposed to match GP, and this delay tau is supposed to match T. If they are perfect match, then the closed loop transfer function will look like this. So this is a very nice formula that basically says when you design the controller, you can ignore the delay, just design a controller GC just for GP. And the end result is you can essentially move the delay outside of the loop. You get the exact dynamics you want. So that's very nice. However, in practice, especially when the gain is high, we see we run into problem. Palmer found out the system, if you design the system and the gain is very high, maybe the nominal system look very nice. However, if you have arbitrarily small deviation, I'm not talking about within certain interval, it is arbitrarily small. The system suddenly may become unstable. And he called that as a practical stability problem. He used the Nyquist stability criterion to demonstrate that's indeed the case. However, if you look at this problem from the neutral time delay system point of view, it is actually a two-delay problem. It is a neutral time delay system with two delays. And when there's a slight mismatch, then you run into the difference equation problem. So how should we look at this problem in actual formulation? Now, different components. This is the plane transfer function. You can write in state space form. And this is the one part trying to mimic the delay. This can also be written in state space form. And the controller that is supposed to be designed only for system without delay can be written in this form. Now, in order to study this sensitivity issue, the core problem is the difference equation. So, in other words, you can ignore the differential equation and the corresponding variable. You just look at the difference equations. And we end up with this set of differential equation. And this differential equation have two delays, even though tau and t may be very close, but if tau deviates from t, no matter how small that is, then they are independent. And we need to use the strong stability concept. So you can eliminate enough variable to write this whole thing into one single equation and with two delays. And if you use the Hale's criterion, then this is your stability condition. That is, within this unit circle, this spectrum needs to be less than 1. So that's a pretty simple criteria. And depending on different assumptions, you can come up with some criteria. So for example, if your transfer function has a perfect match, what happened? Okay. If your transfer function have perfect match, then you come up with this criteria. And that's algebraic criterion, pretty easy to match, to calculate. If it's a scalar transfer function, then this would be the criterion. And if you also have a perfect match of the transfer function, then it will reduce to the original formulation formulated by Palmer. So that's one example that this sensitivity criterion can be very useful. Now, the second criterion is also a very well-known problem. That's a well-posed problem. And if you consider a regular system without delay, and you have a feedback, static feedback. So this is a well-known system with a direct link. And if I minus D, well, D is, you just put all these D matrices into different entry into a bigger matrix. If this is invertible, then you can write this equation into this form. And you can look at, for example, spectrum and say, well, that this system is stable or not. However, it is well known that when D is too large, then you run into problem. For example, as early as 1971, William, in his book, points that out. And this is all because of potential delay. And this problem is also often known as not well posed when D is too large. Now, if you want to have a more thorough analysis, you need to consider delay. You need to consider in the feedback, there's a potential delay. And you can put it back into the complete state space formulation The thing we need to focus on is again the difference equation. Now, this difference equation in the scalar case, Mesmer, Fu, and Iwasaki has already talked about that. An interesting thing is I noticed in their paper, the word pulling out the delay was used as well. Okay. So next problem I want to talk about is the distributed delay feedback control problem. Let's imagine I have a system that has a delay in the input, and my controller uses distributed feedback control. The nature would be the same if you have two delays or etc. But this is one of the problems. Now, such a problem is well known if you think about the finite spectrum assignments. And also, Karatanov has prediction-based feedback control. You end up with a pretty similar formula. And for the Smith predictor we just mentioned, Palmer also proposed the alternative implementation to avoid some of the problems. And that's again the type of formula. So in other words, distributed feedback control is pretty common. Now, how do we implement such a distributed feedback control? Because it's continuous, it's not that easy to implement in practice. And the most natural thing would be, well, if I use a numerical integration formulation, such as Simpson's method, then you would end up with something like this. So we end up with a discrete delay rather than distributed feedback control. However, when you do that, the nature of the system has been changed, and it has been studied by a few scholars at that time. And one of the most striking phenomena that was observed was by a paper by Van Asch and Engelbart on a very simple system. For this system, if you design feedback control, then you place the pole, there's only single pole at -1. And the system is always exponentially stable, obviously. However, if you do a numerical simulation, and if the delay equals 1, well, they find out the system always is unstable. And what happened? Well, the answer is a lot of people already pointed out is because of the nature has been changed. The numerical simulation is a discretization. So effectively, you change the system into system of neutral delay. And this system has been declared as one of the open problems by a survey paper by Richard. And Mondier and some other people proposed some safe implementation to avoid this problem. Now, there are some stability conditions proposed. For example, Mondier and has a paper that gave a sufficient condition. And this condition, if you apply to this system, you end up with this number. the delay cannot be less than this. And this is obviously less than 1. So that sort of explains that phenomena. Now, another paper by Keqin using a criterion called W stability that gave a stability condition of around 0.4054. That's obviously also less than 1. That can explain that problem as well. And the question is, who's right? Is this the right answer or this is the right answer? Well, it turns out both answers are correct and different assumptions. So let's look at this criteria, this condition. Now, if you look at the equation only involve U, which is the feedback, that is the part we eventually will discretize. And that's the internal dynamics of U. And you can calculate the characteristic equation. Then this is theorem that is basically same as Mondier's paper. It says the internal dynamics feedback is exponential and stable. If that's true, then the complete feedback system with a discrete implementation is also exponentially unstable for sufficiently small fine discretization. So that's basically the idea. Now, in order to make this stability limit tight, what is the requirement is you need to have a conventional delay. In other words, in the discretization, the delays needs to be proportional to each other. But we cannot allow errors. The proportional relationship will have to be guaranteed by structure. We can imagine how to implement that if you have a device which is multi-channeled and it can have a delay in all the channel, exactly same delay. Then you can imagine I can feed one channel to another channel, etc. You can implement that. Now, if you do a numerical simulation, then you will have to use matrices, a big matrix with the same delays. So in terms of formulation, it looks like this. So basically, all the delays are kh, and this h can allow some errors, but they must be the same for all the delays. So that's an important restriction. And a standard reformulation, if you say I want to introduce a variable with all the channels with delays, then you end up with this state space formulation. And this is a big vector. All the delays are the same. So in the last channel, the delay, because it will have to come from here, this delay may be different. However, because this difference equation, the last column is 0, so this delay doesn't really affect anything. So I'll skip the technical details. The basic idea is to say the condition for exponential stability of the difference equation is this matrix, which is one part of that big matrix. Yeah, it's this part of the big difference equation. the spectrum radius must be less than 1. So that's a condition. Now, for that particular example, which is a scalar, we can actually come up with a more explicit formula. This will end up with a polynomial formula, and you can actually calculate that. Okay, so that's the criterion. Now, if you look at this problem again, this criterion become this. And if you calculate that, that's exactly the requirements. And now let's do some numerical calculation. K is the number of intervals, the number of discretization, and this is the maximum delay you can tolerate if you only consider difference equation. And this is the maximum delay you can calculate according to complete discretizer Lyapunov-Kulusovsky functional method. And those are the numbers I get. Now for the coarse discretization, you do not have too much pattern, but as the discretization becomes finer and finer, you can see for the difference equation, you indeed approach that formulation. For the complete system, well, you can the trend is also pretty clear. Although the calculation is kind of costly, so after that it's difficult to continue. So this shows the difference equation is the problem in this formulation. Now, if you allow rationally independent delay, then there's another constraint that says if this matrix transfer function, the spectrum is larger than 1, then the feedback control with the discretization is rationally independent, rationally it's exponentially unstable when the discretization becomes finer and finer. And the idea is when you formulate that, now each delay must have independent delay, independent error. And in this case, you end up with this formulation, and each of these edge are independent delays. So if you go back to this formulation, then the criterion becomes this. And it can be the limits would be this equation, and you can calculate that's exactly the condition Keqin got. And I only do the discretization, the difference equation, and the trend is also pretty clear. But for complete system, it can be calculated again. It's actually pretty close to this formula. Now, the second part of this talk is on computation. Well, it looks like my time is very limited, so I will have to be very brief. Well, for complete quadratic Lyapunov-Kulusovsky functional, it will have to be discretized in order to numerically implement it. And currently, there are two different methods we can do that. One is discretization, another is SO, uh, uh, sum of square method, studied by Matthew Peat. For discretization, then the gist of it is this. The LMI, I have two LMI with this, and n is the number of differentiated variable, and m is difference variable. This formula is only for one delay, but for multiple delays, the idea is very similar. And imagine if you have a system with a delay channel two-dimensional, and m, the differentiated variable has 20 variable, and I divide the delay into 5 intervals. Uh, if you use the traditional formulation versus coupled differential difference equation formulation, then the LMI order would be 32 versus 140 and 50 versus 140. And also the calculation solving LMI is roughly cube of the order of LMI, so that you end up with about almost two order of magnitude of computational difference. So in practice, it's a very striking effect. So the next question is, how do we reduce the order of delayed channels? The first method is ad hoc method. For example, if you have system like that, and as the most practical system will be, B is highly singular, so the rank is much less than n. But a simple trick is write this B into B and C, and you can write that into coupled differential difference equations that will have the effect of reducing the delay channel. The second method is pulling out the delay. It turns out during the modeling stage, if you just make a careful observation of delay, then that's probably the simplest way of coming up with a system with low dimensional delay channels. But the rest of the talk, I will concentrate mostly on decomposition method. And I will also, and this is the formulation. The idea is I want to decompose this system into two different subsystems. And so the idea is make a variable transformation of x and y. So you end up with two subsystems. And what I'm hoping for is to decompose the system. In other words, my second subsystem is independent of the first subsystem. What we need would be this matrix needs to be 0, and this matrix needs to be 0. So that's basically the idea. And those are the formulations. What we end up with is this requirement, this A matrix. If you give me an A matrix, I need to find this block diagonal matrix, and hopefully the number of columns is less than number of rows in some of this matrix. If that's the case, then you can do a decomposition. But if you look at this equation carefully, this basically says if you multiply this matrix by this matrix, you end up with, this is the same matrix, So the right-hand side is each column is a linear combination of the same matrix. So this concept is known as invariant subspace. And this invariant subspace problem has a special structure because you restrict this matrix to be block diagonal. So in a more abstract formula, you need to look at this formulation. Uh, this W is a subspace, and this is a external direct sum of the component subspace. Now, there are two invariant subspace that's always there. One would be zero-dimensional space. Another is a whole subspace, a whole space. So these two are always there. And these are known as trivial invariant subspace. Now, if you can find a structure invariant subspace that is non-trivial, not one of those, then you would find a decomposition. Now, I just give one simple example. Let's say I have a retarded time delay system, and then I can reformulate that. This is called a cascade delay. Stack all the delays. You end up with this coupled differential difference equation. And in order to find the decomposition, the structured invariant subspace, first you find the first component. And the condition turns out this subspace needs to be invariant for all the A matrices. If that's the case, then you can choose the remaining part very easily. First, choose the last component, just between this and this. Once this is chosen, you can go one step at a time. Eventually, you find all the subspace, and then you get that decomposition. A very interesting observation is this. Now, there's a one V naught that always work. That is, I can choose V naught to be zero-dimensional subspace. Then this is always satisfied. And uh, from there, the rest of the subspace can be written in this form. And then you can decompose the system into two parts. This is a subsystem, this is a subsystem. Now, in this case, subsystem 2 is independent of subsystem 1, and subsystem 1 does not have a differential equation, only difference equation. But if you look at that more carefully, it is basically a linear combination of the variable of the second subsystem. Even though this may look like using the first subsystem, but that's a delayed version, and they are not the same. You can use substitution from this to the next. Eventually, you will find out you can express all the variables in terms of the delayed version of this variable. So there's no dynamics. Therefore, there's no stability problem, and you can just ignore this subsystem in your stability analysis. And the system, the reduced order system can be further decomposed, and the neutral type system can be done in the same way. The more general case, this algorithm that's possible. However, in order to successfully implement that, we require the repeated eigenvalue of any matrix involved must have one single Jordan block. For example, if you end up with a matrix like that, then the automatic algorithm will not work because you have an infinite number of one-dimensional subspace. And over there, you will have to use a human judgment or through permutation, hopefully to avoid this problem as much as possible. Even, even though the presence of those give you more possibility, but it's difficult to automate those. So finally, I will give one example. Let's say this is a system and using structured singular value, structured invariant subspace, you end up with this, this, and this matrix. The rest of them, in order to make this guy non-singular, you can put any matrix possible to make this matrix non-singular. Same thing here. And after decomposition, one part of the system can be discarded. You end up with this system with those coefficients. And you can further decompose the resulting system. You go through the same system, same process, but this time you want to decompose rather than just reduce the order. And those are the solution from the structured singular value problem. And you end up with this subsystem and this subsystem and with these coefficients. And finally, we calculate, we do some calculation to find out how much time savings. Now, this is the original system. If you want to use discretized Lyapunov-Kursovsky functional, this is the amount of time you need to spend. After you reduce the order, then we are almost 2 order of magnitude savings. If you further decompose, then each of them needs to be analyzed, and the result is a smaller delay. And we can find out the actual time is about 15 seconds versus 53 seconds. So it's about, I guess, less than 30% of the time needed. So that's basically the idea. Okay. Now I want to thank some of the collaborators and discussions. Silvio Niclasco was the one who introduced this idea to me, and bigger promoter of this formulation would be Vladimir Razvan, and I also worked with Dr. Hongfei Li and Matthew Pete. Some of the former students who worked on this topic are Yi Liu and my current students, Huang Fan Wang, and visiting student Yashen Zhang. Okay, well, that's all I have. Thank you very much. Any questions?
Thank you very much, Professor, for the very nice talk.